Right now, galaxies you could find with a small backyard telescope are leaving for good. The space between us is growing faster than their light can cross it, and past a certain distance, nothing we build can ever reach them. So the edge of the universe is not a wall out in the dark. It is a line drawn by what can still reach us. And most of what you can see in the night sky is already on the far side of it, still glowing, already gone. That same line turns up everywhere we look, out at a frozen moon with a buried ocean, out where our oldest machine is going quiet past the planets. And every edge we reached, we found the same thing waiting. What was it? In 2008, a team led by the astrophysicist Alexander Kashlinsky reported the opposite. Hundreds of distant galaxy clusters sliding the same way, toward a single patch of southern sky, in a coordinated drift the rules we trusted should have forbidden. You, the Earth, and the Sun travel through that ancient glow at about 370 kilometers a second, a little over 200 miles a second, fast enough to cross the United States in roughly 11 seconds, headed toward a point in the constellation Leo. When this lopsidedness first surfaced in the data, the people who found it suspected their instrument before they suspected the sky. The glow runs a fraction warmer and bluer in the direction we are going, a fraction cooler and redder behind us, and that single tilt is our own velocity written across the whole sky. No experiment on a workbench can pick out true rest from steady motion. The universe still keeps one frame apart from all the others, the one in which that first light looks even in every direction, and our speed against it is the single motion that is not just relative to some other thing. What Kashlinsky's team claimed ran faster and made far less sense. Hundreds of clusters, each holding thousands of galaxies, leaning together at close to 600 kilometers a second, fast enough to cross that same continent in about 7, all aimed at nearly one spot across distances where light from a single cluster spends most of the universe's lifetime reaching the next. They named it dark flow, not for any menace, but because, like dark matter and dark energy before it, the cause had no face. Our galaxy is falling, along with 100,000 others, toward a dense region a few 100 million light-years off in nearly that direction. We have since charted that entire basin of streaming galaxies and named it Laniakea, a supercluster so wide that light, the fastest thing there is, needs 520 million years to cross it, longer than animals have existed on Earth. Its currents all drain toward one gravitational low we call the Great Attractor. For decades we could barely study it, because it lies behind the crowded disk of the Milky Way, screened by our own galaxy's stars and dust in a stripe of sky astronomers call the zone of avoidance. A pull like that has a signature. It rules nearby, then loosens its hold, the motion scattering and canceling the farther out you measure. The dark flow drift refused to loosen. It kept one heading past Laniakea, past every structure we can chart, as if its origin lay outside the visible universe entirely. Clocking the speed of something too far to watch move takes a quiet trick. When a cluster drifts through the background glow, the hot gas inside it nudges the light passing through, lifting it slightly on one side and dimming it on the other, the way a swimmer leaves a wake in otherwise still water. One wake drowns in the noise. Stack the light from thousands of clusters, and a shared direction stops hiding. The arrow they measured pointed past the horizon, toward matter that inflation may have flung beyond view in the first fraction of a second, when a patch smaller than an atom was stretched wider than a city before the universe finished its opening moment. Inflation already tells us the true universe dwarfs the part we can see, by a margin so wide the visible cosmos could be 1 grain of it. A real dark flow would be the first direct tug from that hidden remainder, evidence that our patch leans on a mass we are built never to find. The whole framework we use to weigh the universe, to date it, to model how it grows, assumes that on the largest scales it is smooth and the same everywhere, with no favored direction. A bulk flow running across billions of light-years would crack that assumption, and with it, some of the confidence behind every number we quote about the cosmos. The pushback was that fierce for a reason. It was never really about 600 clusters. It was about whether the ground under all our other measurements sits as level as we need it to. The expansion of the universe is speeding up, so past a certain distance the space between us and a galaxy lengthens faster than its light can cross it. We still see those galaxies tonight by light that left long ago, yet nothing they send now will arrive, and nothing we ever launch will reach them. Of every 100 galaxies in your sky, the careful estimates allow us about 3. The other 97 are already gone, still burning in the lens, already past the only edge the word has ever named. 2 cosmologists, Lawrence Kraussett and Robert Scherer, followed that future to its end. Long before it arrives, our own galaxy will have collided and merged with Andromeda into a single elliptical sprawl, the local group folding into one island of stars. Roughly 100 billion years from now, more than 7 times the present age of the universe, every galaxy beyond that island will have crossed the horizon and faded past any instrument, and the background glow itself will have thinned below detection. Astronomers alive then will see one lone city of stars adrift in still, featureless black, and conclude, with flawless reasoning and total error, that it is the whole of creation and always was. Every clue we are reading tonight will be gone. We are awake in the narrow window when the edge can still be read at all, and most of what it could have told us has already slipped away. If that edge is set only by what can still reach us, does the universe carry any edge of its own, or does it simply keep going? Fly in a perfectly straight line and never turn. One of 2 things happens, and most people only ever picture the first. Either you push on through endless new space without end, or you eventually strike some kind of wall, a final boundary to everything. There is a third possibility, and it is the strangest of them. You could travel dead straight, never curving, never stopping, and arrive back exactly where you began, looking at the back of your own head. Which of the 3 is true comes down to a single property of the universe, its shape. And that shape can be measured without ever leaving the room you are in. You do not need to step outside the universe to measure its shape, which sounds impossible until you remember how surveyors have always worked. Draw a triangle on a flat tabletop and add up its 3 corners, and they total 180 degrees every time. Lay that same triangle across the surface of a ball, and the corners bulge past 180. On a saddle, a surface curving the other way, they fall short. The curvature of a surface leaves its mark inside any triangle drawn on it, and you never have to lift off the surface to read that mark. We proved the Earth was round this way long before anyone flew above it. Space can curve in those same 3 ways, and the only thing we ever lacked was a triangle wide enough to test the whole of it. We found that triangle in the oldest light. When the cosmos was young and hot, it left hot and cold patches of a known size stamped across the entire sky. Those patches form the far side of a triangle whose near corner sits at your eye, and how large they appear depends on how space bent along the way. In a closed universe, the patches would look swollen, wider than they should. In an open one, they would look shrunken. We measured them at close to 1 degree across, twice the width of the full moon, the exact size flat space predicts. The universe, as far as the sharpest instruments can read it, is flat to within a fraction of a %. A triangle with sides stretched across tens of billions of light-years still closes to 180 degrees, with no bulge and no sag we can detect. Before the universe cooled, light and matter were fused into a glowing plasma, and pressure waves rolled through it like sound through air, racing outward at a little over half the speed of light. When the plasma finally cleared and the light broke free, those waves froze where they stood, locking one preferred distance into the matter of the cosmos, close to 500 million light-years, from crest to crest, 5,000 times the width of our own galaxy. We read that same spacing twice. Once printed into the oldest light, and again in the way galaxies cluster today, very slightly more likely to sit that distance apart than any other. One ruler, laid down in the first moments, still legible in two completely separate maps of the sky. Flat sounds like the dull answer, the setting the universe was left on by default. It is the opposite of dull. Curvature feeds on itself. The smallest departure from flat in the early universe would have ballooned as the cosmos expanded, the way a hair of error in your steering widens into miles off course. For space to still read flat now, it had to begin flatter than one part in countless trillions, a balance so fine that nothing in the early recipe accounts for it. The leading repair is inflation, that ferocious stretch in the first instant. Blow up a balloon and any small patch of its skin looks flatter the bigger it grows, and stretching a region of space by an unimaginable factor irons whatever curvature it had nearly out of existence. Flatness, in that account, is not where the universe started. It is the scar left by an expansion violent enough to smooth the geometry of everything we can see. Measuring flat still does not answer the question we began with. Flat space can run on without end, but it can also be finite and quietly wrap around on itself, the way the screen in an old arcade game carries you off one edge and back in from the other, with no wall anywhere. A universe built like that would send a straight beam of light the whole way around and home again. If ours wraps, the light should give it away, because we would catch the same stretch of early sky in two directions at once, a hall of mirrors leaving matched rings on opposite sides of the heavens. We combed the oldest light for those matched circles and found none. Either the universe does not wrap, or it wraps on a scale larger than the 93 billion light-years we can survey, which is its own quiet way of staying out of reach. For a long time, the shape was thought to fix the fate, a closed universe doomed to collapse back inward, an open one to thin out forever. Dark energy cut that link. A flat universe, once expected to coast almost to a stop, will instead expand without end and speed up as it goes. Then the clean picture cracked. In 2019, a careful reanalysis of the oldest light, taken on its own, leaned faintly toward a closed universe after all, a weak preference for those patches looking just slightly swollen. Folded in with other surveys, the balance tips back to flat, and most cosmologists still read it as flat. No measurement can ever land on perfectly flat. We can only say flat to within some margin, and a universe curved a hair below that margin would be finite and closed, and so enormous that the slice we see looks ruler straight. By the numbers we hold now, if it curves at all, the radius of that curve runs at least several times wider than everything we can observe, a sphere so vast that 93 billion light-years is a short walk across it. I find that the honest shape of the answer. We did not prove the universe goes on forever. We proved that if it ends, the ending lies further out than any triangle we will ever draw. And one last fact closes the straight-line trip for good. Even in a flat universe with no end, you could never fly that line to check. The expansion is still opening fresh distance ahead of you faster than any ship could ever eat it. So the far side, if there is a far side, pulls away from every traveler forever. The edge in space, curved or flat, finite or endless, is sealed off either by geometry or by speed, which leaves a single edge we can still move toward, not outward across space, but backward through time, into the oldest light itself. How far back does that light reach before it simply stops, and what is sitting at the far end of it? You have never once seen the present. The light off this page, the face across the room, the sun overhead, all of it reaches you a little late, the sun's warmth already 8 minutes old by the time you feel it. Look farther and the lateness grows. Betelgeuse, the red shoulder of Orion, shows you light that left roughly 600 years ago, and if that star tore itself apart a century back, we would have no way of knowing yet. Push outward, and the rule never bends. Distance is age. The deeper you stare into space, the younger the universe you are looking at becomes. That opens the one direction the last two questions left standing, not out across space, but straight down a beam of light into the cosmos when it was new. The thing that turns distance into a clock is the stretch of the light itself. As the universe expands, it pulls the waves of light traveling through it longer, the way ink dots on a balloon spread apart as you blow it up, while the dots themselves never move across the rubber. Light that leaves a young galaxy a sharp ultraviolet can arrive, after billions of years of that stretching, as deep infrared, its waves drawn out more than 14 times longer than when they set off. The size of the stretch is a direct reading of how much the universe has grown since the light departed, a clock you can aim at the sky. It is also why the first galaxies stayed hidden for so long. Their light had slid clean out of the colors our eyes and older telescopes could gather, down into the infrared, where you need a cold mirror in space built to feel heat rather than catch glare. The early universe is thick with neutral hydrogen, and hydrogen drinks light below a sharp cutoff, swallowing everything bluer than one particular line. A galaxy from the deep past arrives with a clean edge in its light, bright on one side of that cutoff and abruptly black on the other. So astronomers photograph the same patch of sky through a row of filters, blue through red, and hunt for an object simply missing from the blue frames that snaps into view in the red. The wavelength where it disappears tells you how far the cutoff has stretched, and that stretch tells you the age. You find the oldest galaxies not by what they show you, but by precisely where their light goes dark. One of the first objects pulled from that infrared deep was a faint red smudge called HD1. Its light had been traveling for around 13.5 billion years, setting out when the universe was roughly 330 million years old, less than 1/40th of its present age. Map the whole story of the cosmos onto a single year, and this light left in the first week and a half of January. The distance hides a twist. HD1 is not 13.5 billion light-years away now. Space kept expanding the entire time its light was crossing, so the galaxy itself sits closer to 33 billion light-years off today, far past anything we could ever reach. And whatever HD1 became, it had all those billions of years to do it while the light crawled toward us, long enough to grow, merge, or burn out completely. We are not seeing a galaxy. We are seeing a rumor of one, delivered impossibly late. Those record breakers brought a problem with them. The galaxies we keep turning up in the first few 100 million years look too far along, too bright, and too built up for the little time the universe had to make them. Stars need time to gather, ignite, and pile into something massive, and several of these early galaxies seem to have managed it impossibly fast. The possible fixes are themselves a tour of the unknown, that the first stars were monsters far larger and brighter than any forming today, that black holes were already feeding at their centers and outshining all the stars around them, or that our model of how quickly the young universe could build is simply wrong. Some of the boldest early candidates, measured with more care, turned out to be nearer galaxies wearing a disguise, their distances overstated. Enough have survived the scrutiny to keep the problem wide open. What unsettles me is the direction of the surprise. The record does not inch forward. It keeps breaking the wrong way, toward galaxies with no business looking so finished so soon. Push this time machine as far as it will go, and it stops hard against a wall. Run the clock backward, and the universe grows hotter and denser until, before about 380,000 years, it was a glowing fog of bare particles, too hot for atoms to hold. Light could not cross that fog. It scattered off loose electrons the instant it moved, the way headlights drown in heavy cloud. When the fog cooled enough for the first atoms to form, the light broke free all at once and has streamed ever since, stretched now into that faint background glow we keep coming back to. Astronomers call that moment the surface of last scattering, the last time light ever touched matter before flying loose. That glow is the oldest light there is, not because nothing came before it, but because before it the universe was opaque, and no light from earlier can ever reach us. The edge in time is not a fading, it is a curtain. There is a gap on this side of the curtain stranger than the curtain itself. When the fog cleared, there were no stars yet, only cooling hydrogen in the dark. For somewhere between 1 and a few 100 million years, a whole era with no sources of light at all. We call it the cosmic dark ages, the one long stretch of history that left almost no light to read, which is why we are now learning to listen for it instead, for a single faint note from hydrogen at a wavelength of 21 centimeters, stretched today into meters. So the deepest galaxies we can find, HD1 among them, are not the beginning. They are the first lamps lit after a long darkness, caught in the narrow band between the curtain and the dawn. Those first lamps did more than end the dark. The earliest stars were built from nothing but hydrogen and helium, and in living and dying they cooked the first heavier elements the universe had ever held, the carbon and oxygen and iron that everything afterward, including you, is made from. HD1 is an entire galaxy of them, far too distant and too faint to break apart into single stars. Across that much space and that much time, could we ever catch the light of just one of those first stars, standing alone? Across nearly 13 billion years of space, you should not be able to see a single star. A whole galaxy at that distance is a faint smear, the merged glow of 100 billion suns crushed into one dim point, and until recently the only individual stars we could pick out were the ones inside our own galaxy and its near neighbors. Pulling one star out of the deep past is like standing in New York and trying to read a single candle flame in a window in Tokyo. Yet in 2022, that is what turned up, the light of one star, alone, that set out when the universe was about 900 million years old, less than a 14th of its present age. The discoverers named it Earendel, an old word for the morning star, the first light before dawn. Seeing it at all took the universe bending its own light. Mass curved space on the largest scale and barely showed it. Up close, around something heavy, that same curving turns sharp, and a massive object warps the space around it into a lens. Einstein worked out that gravity must bend light, then doubted such a lens could ever be useful, because the alignments would be far too rare. Whole clusters of galaxies turned his rare case into a tool. Between us and Earendel sits an enormous cluster, and its gravity, most of it dark matter, focuses the light of everything behind it. Along certain lines through that lens, called caustics, the focusing runs to an extreme, stacking the light of a background object thousands of times brighter than it would be alone. Earendel rides inside a background galaxy the same lens has smeared into a long glowing streak. The sunrise arc, and the star sits at the single most magnified point along it, the difference between a candle lost on the far side of an ocean and that same candle suddenly bright enough to find. That alignment is a knife edge, and it does not hold still. As the cluster and the star drift across our line of sight, the magnification climbs and falls. So, a star caught this way can brighten and fade over years, flaring into reach and slipping back out. We caught Earendel inside its window. It was not the first star found this trick, only the farthest. 4 years earlier, the same lensing had pulled out a star nicknamed Icarus, its light about 9 billion years old, and at the time that looked close to the limit of the possible. Earendel pushed the record almost 4 billion years deeper, and a small, growing catalog of these lens stars has followed it since, each one a brief alignment we happened to be watching when it happened. Earendel itself is a furnace. The light points to a massive blue-white star burning at something like 20,000 degrees at its surface, more than 3 times as hot as the sun. Stars that hot live fast and die young. Where the sun will burn for 10 billion years, a star like this spends itself in only a few million, a short, violent sprint that ends in collapse. So the star is long gone, dead for billions of years, and the light we caught is the last thing left of it. Set it beside our own beginnings. By the time the sun and the earth first formed, this star's light had already been crossing space for more than 8 billion years, with billions still to go before it reached a planet that did not yet exist. The deeper hope behind a star like Earendel is that it might be one of the very first. Astronomers sort stars into populations, and the numbering runs backward against intuition, with the youngest metal-rich stars like our Sun labeled Population 1, the older metal-poor stars Population 2, and the original stars, built from nothing but the hydrogen and helium the Big Bang left behind, called Population 3. Those first stars are thought to have been giants, blazing and short-lived, and in dying they forged the first carbon, oxygen, and iron the cosmos had ever held, salting empty space with the ingredients of everything after. Earendel is early, but probably not that early. By its era, the universe had already made some heavier elements, so the star likely carries a trace of them, which keeps it just shy of truly pristine. No truly first star, metal-free and alone, has ever been confirmed. Why the first stars grew so large comes down to what was missing. A cloud of gas collapses into a star only when it can shed its heat and cool, and metals are what let gas cool quickly and break into many small clumps. With no metals at all, the earliest clouds could barely cool. So instead of fragmenting into many sun-sized stars, they fell together into a few enormous ones, some perhaps hundreds of times the sun's mass. Stars that large end in ways smaller stars never do. The most massive may have detonated so completely that they left nothing behind, while others collapsed straight into black holes, possibly the seeds of the giants now anchoring the centers of galaxies. The first generation may have written both halves of the cosmos at once, the elements and the black holes that haunt it. We know what one of those first stars should look like without ever having seen it. It would glow with the colors of pure hydrogen and helium, show none of the lines that metals stamp onto starlight, and lean hard on a particular signal from helium that ordinary stars lack. The new infrared telescopes are combing the early universe for exactly that fingerprint, and so far every promising candidate has turned out to hide a trace of metal somewhere, too faint and too distant to trust. We have written the full physics of these stars, modeled how they lived and burst, named the elements they should have left behind, and never once laid eyes on one. I cannot think of another corner of science this confident about an object no one has actually seen. Every heavy atom in your body was made inside a star and thrown out when that star died. The calcium in your bones and the iron in your blood and the oxygen in every breath, all forged in furnaces like the one Earendel was. When you look at that single ancient point of light, you are looking at the kind of object that built the material you are made of, an explosion upstream of you whose light is only now arriving. Those first stars are gone, but stars are still being born, in clouds scattered across every galaxy, including ours, tonight. And until very recently, we could not watch a single one of them being made. The birth of a star, the most common event in the universe, stayed hidden from us. What was hiding it? It was never the distance. Stars are born deep inside enormous clouds of gas and dust, cold and dense, and that dust is the whole problem. Visible light, the kind your eyes are built for, cannot escape it. A young star buried in such a cloud could be blazing away, and from outside you would see only a dark, dirty smudge against the stars behind it. The cradle is opaque. For most of the history of astronomy, the most common event in the universe was taking place entirely behind a curtain we could not see through. We knew stars had to be forming somewhere in those dark clouds. We simply could not watch it happen. The way through the curtain is to stop using visible light and switch to infrared. Dust blocks light by getting in its way, and whether it blocks depends on the size of the light's waves measured against the size of the grains. The grains are minute, and the short waves of visible light run about the same size as the grains, so they scatter hard against them, especially at the blue end. Infrared waves are several times longer than the grains themselves, and they roll straight past. Picture waves meeting a piling in the water. Short, choppy waves break against it and throw spray, while long, slow swells lift and pass over it as if it were not there. Infrared is the long swell, carrying the heat light of newborn stars out through dust that stops every visible ray cold. The edge we keep meeting in this story turns up here not as a place in space, but as a line in the spectrum, the wavelength past which the universe goes transparent. Point an infrared eye at the right cloud and the curtain turns to glass. One of the first places we did this showed a landscape that looks like a mountain range at golden hour, a rugged orange ridgeline under a haze of stars in a corner of the Carina Nebula about 7,500 light-years away. The light reaching us tonight left around the time people were raising their first towns. The discoverers called the ridge the Cosmic Cliffs, and the name misleads a little. There is no rock there, nothing solid at all. What looks like a cliff face is the edge of a vast cavity, a wall of cold gas and dust being eaten back from the far side, its tallest peaks standing about 7 light-years high, nearly the gap between here and the next bright star. Carina is one of the most violent nurseries in the galaxy, home to Eta Carinae, a monster over 100 times the sun's mass that flung off a huge shell of itself in the 1840s, briefly becoming one of the brightest stars in the sky, and now waits to die as a supernova. Something is doing the eating, and it sits just out of frame. Above the cliffs, beyond the edge of the picture, are massive young stars far hotter and more violent than the sun, pouring out ultraviolet light and fierce winds. That radiation boils the surface of the cloud away, stripping gas off layer by layer and pushing the wall steadily back, hollowing the cavity out. The peaks and spires left behind are the stubborn parts, knots of denser gas that resist the erosion a little longer while the lighter material around them is swept off, the way a desert butte stands as the softer ground wears away beneath it. The most famous version of these shapes rises in another nebula entirely, the towering columns we call the Pillars of Creation, carved by the very same process. At the tip of such a pillar sits a dense knot, sometimes wrapped around a forming star, and a race is underway inside it, the star trying to finish gathering its mass before the radiation strips away the gas it is still feeding on. Some finish in time. Others are left half-built, their growth cut off when the cradle is blown apart. The eating does not only destroy. As the radiation front presses into the cloud, it compresses the gas just ahead of it, squeezing pockets that were stable into collapse, and a collapsing pocket of cold gas is exactly how a star begins. So the same blast tearing the cloud apart is lighting new stars along its leading edge, a wave of destruction with a wave of birth riding inside it. The massive stars carving the cavity will burn out within a few million years and explode, and those explosions will compress the gas further still, setting off yet another round of births. The longer I look at this, the harder it gets to keep destruction and creation in separate boxes. At the edge of this cloud, they are not opposites. They are the same motion, seen from two sides. Behind the dust, in the columns infrared finally opened, the machinery of birth is running. Each forming star sits at the center of a flat, spinning disk of gas, the leftover material that will later gather into planets. While twin jets fire out along its poles, beams of gas thrown light years into space to shed the spin the collapse cannot hold on to. Where those jets slam into the surrounding gas, they light up glowing shock fronts. Knots first catalogued in the 1950s by George Herbig and Guillermo Haro, whose names they still carry. None of it was visible before. The cloud hid the disks, the jets, dozens of newborn stars, all of it lost in the dark until we changed the light we looked with. And the dust is not only a curtain. The same grains that hid the nursery are the raw stock of worlds, the material in those disks that will pebble together into planets. The thing blocking our view of star birth is the thing that builds the planets around them. There is one last way the picture deceives. It looks like a place you could stand in, a fixed landscape held in a photograph. It is not a place. It is a single instant in a process that unfolds over hundreds of thousands of years, a still frame from a film far too slow for any human to watch move. The cliffs are advancing, the stars are igniting, the jets are firing, all of it frozen for us at one moment only because our lives are shorter than a single scene of it. This is one nursery, in one arm of one galaxy, lit a handful of stars at a time. There was an age when the whole universe did this at once, building stars faster than it ever has since or ever will again. What did the sky look like then? The sky then was on fire. Not one nursery at a time, the way our galaxy works now, but galaxy after galaxy, across the whole universe, blazing with new stars at once, at a pace the cosmos has never matched before or since. We can say that with confidence because we can measure how fast the universe has built stars across its entire history, and the record is not flat. It rises, peaks, and falls, a single curve that cosmologists call the cosmic star formation history. The peak has a name. Astronomers call it cosmic noon, the high point of all creation, when the lights came on faster than at any other moment in time. And we live a long way past it. Cosmic noon was not near the beginning, the way you might guess. It came about 10 billion years ago, when the universe was roughly 3 billion years old, only a quarter of the way through the life it has lived so far. Map that life onto a single human span, and the peak of star formation falls somewhere in its early 20s. The climb up to it was steep, the universe lighting fast out of the dark ages, and the fall on the far side has been long and gradual. At the height, the cosmos was forging stars at something like 10 times the rate it manages today, and since then the birth rate has slid downhill, a tide that crested long ago and has been going out ever since. The sky you look up into tonight is a quieter place than it was, running on a fraction of the fire it once held. Measuring the birth rate of the entire universe sounds beyond reach, until you remember that distance is age. A galaxy 10 billion light-years away shows us the universe as it was 10 billion years ago, and a galaxy half that far shows a later chapter. So, astronomers survey galaxies at every distance and count how furiously each is making stars, reading it off the most massive newborns, which burn in fierce ultraviolet and die fast, so their glow can only mean stars formed recently. Sort those measurements by distance, and you have stitched the birth rate of the cosmos together at every age, one snapshot per distance, assembled into the curve that climbs to cosmic noon and falls away after. One of its quiet lessons echoes the last nursery we visited. A huge share of the star formation at cosmic noon was buried in dust, its ultraviolet glow swallowed and re-emitted as infrared, and we undercounted the universe's most fertile age until we learned to measure that heat. The boom was even larger than it first looked. You cannot travel to cosmic noon to watch it, so we do the next best thing and find a place still living in that era. In a small galaxy beside our own, about 160,000 light-years off, sits the Tarantula Nebula, the most ferocious star-forming region anywhere near us, its light leaving around the time our own species was first spreading across the Earth. The tarantula builds stars at the kind of rate that was ordinary at cosmic noon and is rare now, which makes it a living fossil of the universe's loudest hour. At its core sits a cluster so extreme, it includes a star catalogued as R136A1, weighing as much as 200 suns, so heavy that the rules say a star should barely hold itself together at that size, and shining millions of times brighter than the sun. That cluster is not one freak, but dozens of the most massive, luminous stars known packed into a few light-years, the kind of blazing, crowded core that was common when the universe was young. If the tarantula sat as close to us as the nearest large nursery in our own galaxy, it would stretch across a quarter of the night sky and cast shadows on the ground. Something turned the furnace down, and it was not a single force. Stars form from cold gas that can collapse, and over time the universe ran short of it on two fronts at once. The easy gas got used up, locked away inside the stars already made, and what was left grew harder to gather as expansion thinned everything out. The heavier blow came from the stars and black holes themselves. Exploding stars and the violent jets of feeding black holes pump enormous heat into the surrounding gas, and hot gas will not collapse, so the very objects born in the boom warmed their own fuel until it could no longer make more of them. There is a strange order to the shutdown too. The biggest galaxies, the ones with the most gas to spend, burned through it earliest and fastest and went dark first, while the smallest galaxies are still quietly making stars even now. Creation, at the scale of a whole galaxy, carries the seed of its own slowdown. The decline is not coming. It already happened. By most estimates, the great majority of all the stars that will ever exist have already been born, and the universe is slowly winding its star-making down toward a long, dim quiet. The lights will not go out all at once. The smallest, coolest stars sip their fuel so slowly they will still be burning trillions of years from now, long after the last big bright stars are gone. Our own sun belongs to that late chapter. It formed about 4.5 billion years ago, some 6 billion years after cosmic noon, out of gas already enriched and recycled by generations of stars that lived and died before it. We are not the children of the boom. We are built from its leftovers. It took me a while to settle into the order of that. We did not arrive early, while the lights were coming on. We arrived late, in the long dimming after the brightest hours were already spent, and somehow the stars still burning overhead seem rarer for knowing it, not more ordinary. If the universe is past its peak of making stars, then more and more of what it has made is now doing the other thing. Every star that ever ignited is burning through its fuel on a clock, and one by one they reach the end of it. The boom is over, but the dying has barely started, because stars take far longer to die than they take to be born. We have watched a nursery, and we have watched the birth rate of the whole universe across all of history. What we have not done is stand close to a single star at the moment it ends. What does that actually look like? A star like the sun does not explode when it dies. The word death calls up something violent, and this is the opposite, a slow letting go. 2,000 light-years from here, in a faint shell of gas called the Southern Ring Nebula, a star roughly the mass of our sun is in the middle of exactly that ending, its outer layers drifting away in soft, glowing rings. The light reaching us tonight left around the height of the Roman Empire. What looks like a smoke ring hung in space is a star turning itself inside out, shedding everything but its core and lighting the wreckage as it goes. The dying takes its time. When a sun-like star runs low on the hydrogen at its center, it swells into a red giant, fuses its helium for a while, then turns unstable and begins to shudder, pushing its outer layers off in slow pulses over tens of thousands of years. Underneath, the star's bare core stands exposed, a furnace of 100,000 degrees or more, flooding the escaping gas with ultraviolet light. That radiation tears electrons loose, and as they recombine, the gas glows, each element in its own color, oxygen in green, hydrogen in red. The shell does not shine by reflected light. It is lit from within, the way fog glows around a street lamp buried inside it. The shells push outward at only tens of kilometers a second, drifting rather than blasting, which is why the structure stays delicate enough to read. The name for these shells is a leftover mistake. When William Herschel cataloged them in the 1780s, they looked through his telescope like small round disks, the soft color of a planet, so he called them planetary nebulae, and the name stuck even though they have nothing to do with planets at all. They are also fleeting. A star burns for billions of years and then puts on this display for only 10 or 20,000 of them before the gas thins and fades into the dark. Scale the star's whole life down to a single year, and the glowing shell lasts about half a minute at the very end. Every planetary nebula we find is caught at a different point in that brief fade, a whole gallery of last breaths frozen at different moments. For 2 centuries, we pictured one star at the center, quietly dying alone. The sharpest infrared look revealed something else. The star that made the southern ring is not the bright one you would point to first. It is the fainter of 2 stars at the heart of the nebula, wrapped in its own dust, while the brighter companion beside it is younger and still burning. The shape gives away the company it kept. A star shedding its layers all alone should puff out a smooth, round bubble, but this nebula is full of rings, arcs, and ragged shells. When a companion orbits close enough, the swelling giant can engulf it entirely, and the smaller star plows through that shared envelope, spiraling inward and flinging the gas off in loops, the way a spoon drags patterns through cream in coffee. You can read the choreography of an unseen partner in the gas. The death we assumed was a solo turns out to have been a duet, written into the shape of what was thrown off. What is left when the gas clears is not nothing. The core that lit the whole display settles into a white dwarf, the crushed remains of the star packed into a ball about the size of the Earth while still holding nearly half the mass of the sun. The crowding is hard to picture. A single sugar cube of white dwarf material would weigh about as much as a car. It makes no new energy. It sits there and cools, fading over billions of years, so slowly that not one white dwarf anywhere has had time to go fully cold since the universe began. There is a hard ceiling on it, though. If a white dwarf in a close pair pulls in too much extra matter and crosses about 1.5 times the sun's mass, it detonates completely, in a blast so uniform that astronomers use these explosions as measuring sticks across the cosmos. Those very blasts are how we first learned the expansion of the universe is speeding up. The gas drifting away is not the same gas the star was born from. Across its long life, the star fused light elements into heavier ones, and as it casts them off, it salts everything nearby with fresh carbon, nitrogen, and oxygen, and through slow neutron capture, It builds roughly half of all the elements heavier than iron. The barium and strontium and lead scattered into space by deaths like this rather than by any explosion. Out in the cooling shell, where temperatures finally fall far enough, that material condenses into grains of dust, the very same kind that hid the nurseries we looked into earlier and that gathers into the disks where planets form. So the dust that builds new worlds is forged, in large part, in the quiet deaths of stars like this one. What changed the way I see this is the direction the material goes. The death of a sun-like star is mostly not destruction. Most of what the star ever was ends up scattered outward and handed on, while only a small, dense cinder stays behind. The carbon in your cells and the oxygen in your breath pass through endings exactly like this, and in about 5 billion years, the sun will swell past the inner planets, shed a glowing ring of its own, and leave a white dwarf where it used to burn. That scattered material does not stay loose forever. Gravity gathers it back, pulling the enriched gas into new clouds, new stars, new galaxies, the cycle turning over again. But gathering matter on the scale of a galaxy takes more pull than the stars and gas alone can give. It takes the invisible scaffolding we met at the very start, the unseen mass that holds galaxies together, which makes one galaxy almost impossible to account for. Somewhere out there floats a galaxy that seems to have assembled itself with almost none of that hidden mass at all. How? 65 million light-years away floats a galaxy you can almost see straight through. It spreads about as wide as the Milky Way, yet holds so few stars, so thinly scattered, that distant galaxies behind it shine right through its body like streetlights through thin fog. The light reaching us tonight left around the time the last dinosaurs died. It belongs to a class astronomers only recently learned to spot: ultra-diffuse galaxies, spread so faint they were missed for decades, and most of those turned out to be packed with dark matter. This one, named NGC 1052 DF2, runs the other way. What makes it strange is not how dim it is how its contents move. The clusters of stars drifting through it travel slowly, far too slowly for a galaxy of its size, as if nothing extra were pulling on them at all. By every rule we have, that should be impossible, because a galaxy is supposed to be mostly something we cannot see. To feel why that breaks the rules, look at how we know dark matter is there at all. The clue goes back to the 1970s, when the astronomer Vera Rubin measured how stars orbit in spiral galaxies and found the outer stars moving just as fast as the inner ones, when they should have lagged behind, like the far horses on a carousel somehow keeping pace with the near ones. The only fix was an enormous halo of unseen mass, far larger than the visible disk, with the bright galaxy sitting deep inside it, roughly 5 times more of this hidden stuff than all the ordinary matter combined. Every galaxy we have ever weighed carries it, usually far more of it than stars. A small, diffuse galaxy like DF2 should be almost nothing but dark matter, its visible stars a thin garnish on a massive, invisible body. Instead, its star clusters drift at the lazy pace the visible stars alone would produce, where a dark matter-filled galaxy would whip them around several times faster. The invisible body is simply not there. There has always been another way to read the missing mass. Maybe dark matter is a fiction, and gravity itself behaves differently in the thin outskirts of a galaxy, pulling harder than our equations allow, so no unseen substance is needed. That idea has real support, and it earns it honestly, predicting the precise way most galaxies rotate from their visible matter alone with uncanny accuracy. A galaxy without dark matter cuts straight at it. If the fast motion in other galaxies came from gravity working a new way, gravity would have to work that way everywhere, because a law of nature does not switch off in one galaxy and stay on in the next. DF2's stars would still have to race. They do not. The slow drift in this one galaxy says the extra pull is not a rule built into gravity. It is a thing, a substance, that a galaxy can hold a great deal of, or somehow almost none of. The absence is the evidence. The single galaxy that appears to be missing dark matter is among the strongest reasons we have to believe dark matter is real. All of this rests on one shaky number, and it is worth being plain about how shaky. Everything hinges on how far away DF2 actually is, and that distance is fought over. The team that found it placed the galaxy around 65 million light-years out. A rival group argued it sits much closer, perhaps 40 million, and at the nearer distance the galaxy would be smaller and lighter. Its slow clusters perfectly normal, its missing dark matter no longer missing at all, the whole puzzle dissolving into a measurement error. Sharper measurements, using the steady brightness of the oldest red giant stars as a distance marker, pushed back toward the farther figure, and a second galaxy in the same patch of sky turned up looking just as empty. So the case has firmed without fully closing. The strangest galaxy we know might be exactly what it appears, or an ordinary one standing closer than it looks. If the result holds, the next question is how a galaxy loses the very thing every other galaxy is drowning in. The leading answer is violence. Dark matter does not bump into anything. It slides through ordinary matter untouched, so untouched that, if it fills the galaxy as we think, billions of its particles are streaming through your body every second without grazing a single atom. Because it feels nothing. A hard enough collision can split it from ordinary matter entirely. Smash two gas-rich galaxies together at high speed, and the gas slams to a halt and flares into new stars, while the dark matter sails straight on through and keeps going, leaving a galaxy of stars with its invisible halo torn off. DF2 and its twin appear to lie along a trail of such see-through galaxies, the debris of one ancient wreck. We have watched that exact separation on a larger stage. In the Bullet Cluster, two clusters of galaxies collided, the hot gas piled up in the middle, and the gravity, mapped by how it bent the light of things behind it, was found far out ahead of the gas, having passed clean through. Mass and visible matter, caught in the act of parting ways. What I keep having to admit is the size of what we are taking on trust. About 5/6 of all the matter in the universe is something no one has ever held, identified, or made in a laboratory. The favored candidates, from heavy particles called WIMPs to feather-light ones called axions, have each been hunted for years in detectors buried deep underground, and not one has been found. We know the stuff almost entirely by its pull, by the way galaxies refuse to fly apart and clusters bend light around an unseen weight. And the firmest sign that this scaffolding is a real substance, rather than a crack in our laws, comes from one faint galaxy you can see straight through, the rare place where the scaffolding is gone. The thing holding the universe together is something we recognize best by where it goes missing. We have leaned on that unseen mass to hold the largest things in place, trusting a scaffolding we have never once touched. The nearest edge asks the same trust of us. The outer boundary of our own solar system, the shell that marks where the sun's family ends, has never been seen either. We know it almost the way we know dark matter, by inference, from the things that come falling out of it. So how far does the sun's reach really go? And what waits out there in the cold that we have never laid eyes on? The planets are not the edge of anything. They are a tight knot at the center of a solar system that runs vastly farther out, and its true boundary sits where no instrument has ever seen. Wrapped around the entire sun, far past the last planet, astronomers believe there is a shell of frozen objects called the Oort cloud, pictured in two parts, a thicker inner cloud and a thin outer one, whose edge may lie 100,000 times farther from the sun than the Earth is. That distance resists the imagination. Sunlight, which reaches the Earth in 8 minutes, would take well over a year to arrive at the cloud's far side, and our fastest spacecraft, after nearly 50 years in flight, would need tens of thousands more to cross it. The outer edge may reach a third of the way, or more, to the nearest star, so that if other suns carry clouds like ours, the far fringes of our family and the next star's family may nearly brush in the dark between them. And we have never once seen any of it. Like the dark matter we just left, the Oort cloud is something we know almost entirely from what falls out of it. What falls out of it are comets. Not the ones that return every few years, but the rare visitors that swing in once, blaze for a few weeks, and leave on orbits so enormous they will not be back for thousands or even millions of years. Some last appeared before any city stood on Earth, and will not return until long after every language now spoken is gone. Trace the path of one of those long-period comets backward, and it points to a starting place tens of thousands of times the Earth's distance from the Sun. Do it for many of them, and the real surprise appears. They do not come from the flat plane the planets share. They arrive from every direction at once, from above and below and all around, which can only mean the reservoir they fall from is not a ring or a disk. It is a sphere, a vast hollow shell wrapped clean around the whole solar system. We mapped its shape without ever seeing a single piece of it, purely from the angles its stray visitors came in on. The shell is thought to hold something like 1 trillion icy bodies, perhaps far more, each a frozen lump of ice and dust, most no bigger than a mountain, drifting in the dark with miles of emptiness between them. They did not form out there. The cold at that distance is too still, and the material too thin to build anything at all. They were made close in, among the young giant planets, and then thrown out. In the chaos of the early solar system, Jupiter, Saturn, and the ice giants shifted their own orbits and swung past countless small bodies, hurling them outward with their gravity, the way a spacecraft today steals a planet's motion to slingshot deeper into space. Most of those exiles were lost to interstellar space for good, and a fraction settled into enormous, distant orbits. That leftover scatter, the discarded rubble of the planet's own construction, is the cloud we are talking about. We still cannot say how many bodies are out there or what they weigh together, with estimates running from a few times the mass of the Earth on up. Out at the cloud's edge, the Sun barely owns these objects at all. Its gravity, spread across 100,000 times the Earth's distance, has thinned to almost nothing, weak enough that other forces count just as much. The slow pull of the whole Milky Way, what astronomers call the galactic tide, tugs on the cloud from the side, and stars drifting past over millions of years give it the occasional shove. A single nudge can drop one of those frozen bodies out of its lazy orbit and start it falling, a fall that may take 1,000,000 years before the object finally rounds the Sun, flares into a comet, and either returns to the dark or is lost for good. This is not only ancient history. A small star called Gliese 710 is heading our way and will pass through the outer Oort cloud in a little over 1,000,000 years, close enough that it may shake loose a long, slow rain of comets toward the inner solar system, an encounter already written into the motions of the sky. So the edge of the Sun's family is not a wall. It is the place where the Sun's grip fades into the galaxies, where the question of what still belongs to the Sun stops having a clean answer. Every long-period comet, then, is a delivery from the deep past. The bodies in the Oort cloud have sat in the cold and the dark since the solar system formed, barely warmed and barely touched, still holding the original ice and dust of the cloud the Sun was born from. A comet falling inward is a 4.5 billion-year-old sample, sent to us nearly untouched. We may have glimpsed the inner edge of this realm just once, in a small reddish world named Sedna, which loops the Sun on an orbit of roughly 11,000 years and never comes close, swinging out to hundreds of times the Earth's distance before crawling back. Sedna's path is a puzzle in itself. It never comes near the giant planets, so nothing we can see should have placed it on so stretched an orbit, and some astronomers read orbits like it as the fingerprint of a star that passed long ago, or of something large and distant we have not yet found. It still stops me that we have drawn a careful map of something no telescope has ever resolved, working backward entirely from the paths of a handful of visitors that wandered in out of the dark. There is a second, much nearer boundary we will reach later, the edge of the sun's wind rather than its gravity. But that one lies thousands of times closer in than this. The Oort cloud is the outermost edge there is, a sphere we can only infer, dissolving quietly into the rest of the galaxy. Closer to home, though, flattened into the same plane the planets ride in, lies a colder structure we do not have to guess at. We have photographed it, charted its members, and even flown a spacecraft straight through it. What is buried in that frozen ring just past the last planet? Just past Neptune, the planets give way to a different kind of place. Not the spherical shell we just left, but a flat ring lying in the same plane the planets ride in, reaching from about 30 to 50 times the Earth's distance from the Sun. We call it the Kuiper Belt. It was guessed at long before it was seen, sketched out by a few astronomers in the 1940s and 50s, and confirmed only in 1992, when the first of these distant worlds beyond Pluto was finally spotted. We have catalogued thousands since. It is the visible, reachable counterpart to the unseen Oort cloud, close enough that we have photographed its worlds and flown a spacecraft straight through it. Out there, the sun is no longer a disk in the sky, only the brightest star among the stars, and noon on a world like Pluto is dimmer than twilight on an overcast evening here. The belt holds thousands of icy bodies, some hundreds of miles across, drifting in the cold, and taken together they are the wreckage of a planet that began to form and then stopped. A planet should have grown here, and the reason none did is twofold. Building a planet means small bodies bumping gently enough to stick, again and again, until they snowball into a world, closer to the sun, where everything circles faster and packs in tighter. Those gentle collisions happened constantly, and the inner planets pulled themselves together in only millions of years. Out at this distance, the bodies are spread thin and crawl along enormous slow orbits, so collisions are rare, and the same process here would take longer than the solar system has existed. Then Neptune made it worse. As the giant planet settled in and shifted outward early on, its gravity stirred the belt, raising the speeds of the bodies until they no longer kissed and stuck, but slammed and shattered. Neptune also threw most of the raw material away. The belt is thought to have once held tens of times the Earth's mass, and by some estimates more than 99% of it is gone, flung outward to seed the Oort cloud or hurled clean out of the solar system. What remains adds up to a fraction of a single Earth scattered across a volume billions of miles wide. The same wandering that starved the belt left its signature stamped into the orbits out there. As Neptune migrated outward, it swept many of the surviving bodies into step with its own motion, locking them into rhythms that have held for billions of years. Pluto is the famous one. For every 3 trips Neptune makes around the sun, Pluto makes exactly 2, a steady 2 against 3 beat that keeps the worlds forever out of each other's way. Pluto's orbit actually crosses Neptune's, and without that lock the larger planet would have flung it away long ago. The rhythm is what protects it, the way 2 runners can lap a track at a fixed ratio and never meet. A whole class of bodies, the Plutinos, shares Pluto's beat, and roughly a fifth of the larger known objects out there march to Neptune's timing one way or another. Reading those locked orbits is how we trace the path Neptune took on its way out, an ancient migration written in the timing of distant worlds. What the belt failed to build is exactly why it matters. Its bodies are leftover planetesimals, the half-finished building blocks of planets, kept in deep cold instead of melted and reshaped inside a world. The most untouched of them sit in a quiet band Neptune never reached, on nearly circular orbits, moving slowly, undisturbed since they formed. These cold, distant objects are the least altered material anywhere in the solar system, holding the original ice and dust almost exactly as it was 4.5 billion years ago. Many of them travel in gentle pairs, two objects circling each other slowly, and most wear a deep red stain, the mark of simple ices cooked over eons by faint sunlight and cosmic rays. Everywhere else, the early record was erased, rock crushed into planets, heated, melted, churned. Out here it was frozen and set aside. The Kuiper Belt is less a graveyard than an archive, a shelf of original parts left out where the rest of the system long ago threw its first drafts away. This shelf is also what cost Pluto its title. For most of a century, Pluto was the 9th planet, a lone small world at the edge. Then, through the 1990s, we began finding others like it out there. And in 2005 came Eris, about Pluto's size and deeper out, nicknamed half in jest after the goddess of discord. The discord was real. Pluto was not a lone planet after all, but one of the larger members of a crowd. And calling it a planet while ignoring the rest no longer held together, so the definition was redrawn, and Pluto became the first of a new category. I grew up with 9 planets, and I noticed the small resistance that still rises when Pluto is called something else. We did not shrink Pluto. We finally saw the crowd it had always been standing in. Our tidy picture of the solar system was never wrong so much as incomplete, an artifact of not yet being able to see far enough. The belt is not entirely still. The giant planets keep nudging bodies loose, and many of the comets that swing through the inner solar system on short, regular orbits began their fall right here, the closer cousins of the long-period comets from the Oort cloud. But the real prize is the frozen parts themselves, because the unbuilt blocks can show us how building actually works. For decades, 2 camps argued it out on paper, the violent and the gentle, with no way to look at an untouched block up close, no way to know whether worlds are slammed together out of force or drift together out of something far quieter. If we could reach one of these undisturbed objects and look at it closely, it might end the argument for good. So we went. What did we find when we flew up to one and looked? On the first day of 2019, a spacecraft the size of a piano swept past the most distant object anything from Earth has ever reached, 4 billion miles out in the Kuiper Belt. The craft, called New Horizons, had launched 13 years earlier as the fastest thing we ever threw off the planet. And its target out here was so faint it was not even found until after launch. The thing it flew past, named Arrokoth, looks like a snowman someone sat on. 2 rounded lobes joined at a narrow neck, the whole of it about 22 miles long, the length of a fair-sized city. Arrokoth means sky in the language of the Powhatan people. It is a cold, dark, frozen lump, and at first glance nothing about it is dramatic. But it was the target on purpose. We crossed the entire solar system to study it, because a body this small and this untouched might finally settle a question we had argued over for decades, with no way to decide it. How do worlds begin? Planets, the picture went, are built from the bottom up by collision, dust sticking to dust, pebbles to pebbles, the growing clumps smashing into one another harder and harder until, after countless impacts, a world takes shape. The trouble is that the picture breaks in the middle. Once a clump grows to about the size of a boulder, the collisions stop helping. At those sizes, 2 rocks meeting at speed tend to shatter or bounce apart rather than stick. Worse, a body around a meter wide feels a headwind from the gas in the disk and spirals toward the sun in only a few hundred years, far too fast to wait around growing. The clock and the collisions were both working against it. Something had to carry matter across that gap gently, without the speeds that destroy, and the other camp argued for exactly that. For years, it stayed a fight on paper, because no one had ever seen an original building block up close. Arrokoth answered by what it lacks. If its two lobes had crashed together at high speed, the seam between them would show it, crushed, fractured, deformed, the way a car carries the wreck it was in. The neck is undamaged. The two lobes sit flush against each other, gently, with no sign of compression, and the whole body turns slowly, once every 16 hours or so, not flung into a wild spin the way a hard merger would leave it. There were other tells. Both lobes are strangely flattened, like two pancakes, and their flat faces line up, the matching pose you get when two objects settle together slowly rather than collide at random angles. Run the numbers back from all of that, and the two pieces came together slower than you walk, a soft touch at the end of a long, patient approach. What gets me is the size of the evidence against the size of the witness. The whole question of how worlds begin came down to whether a seam on a 20-mile lump showed bruising. It showed none. In the disk of gas and dust around the young sun, pebbles do not only collide. They can pile up in slow eddies, gathering into a dense local swarm, until the swarm grows heavy enough to pull itself together under its own gravity and collapse straight into a solid body. No high-speed smashing. A swarm of pebbles draws together under its own weight in one quiet collapse, more a gathering than a crash. Often that collapse makes not one body but two, a pair born together, circling each other closely, slowly losing energy until they drift in and meet at walking speed. The idea makes a prediction we can check. If planetesimals form in pairs this way, gentle binaries should be common among the most pristine bodies out here, and they are. Roughly a third of the undisturbed Kuiper belt comes in pairs, exactly as a quiet collapse would leave them. Arrokoth is one of those pairs, finished as a soft contact binary, and it crosses the barrier the old story stalled at because it never needed a violent collision at all. And Arrokoth held still long enough to keep the receipt. It belongs to that undisturbed band of the belt Neptune never stirred, so it has drifted in the deep cold, near 230 degrees below zero, since the solar system was new, never heated, never knocked about. Its surface is smooth, with almost no craters, the mark of a quiet life in a thinly populated stretch of space, which is itself a clue, telling us the early belt out here was sparse and slow, not a shooting gallery. It is also a deep uniform red, stained by complex organic molecules built up over billions of years as faint sunlight and cosmic rays worked on its ices. Those red organics are not only a stain, they are the kind of carbon chemistry that has to exist before anything more interesting can, sitting on a surface untouched since the beginning. What we flew to was not a relic of formation. It is formation itself, paused at the end of the very first step, and frozen in place for 4.5 billion years, waiting. The spacecraft tore past at more than 30,000 miles an hour, with no way to stop, snatching its images in a few hours and then trickling them home across 4 billion miles so faintly that the full set took nearly 2 years to arrive. Hitting a 20-mile target that far out after a 13-year flight on a single fast pass is a kind of marksmanship that still does not quite feel real. We waited 2 years to learn that worlds begin softly. But this same spacecraft, years before it reached the little snowman, had already flown past something far larger in this belt, a world we expected to be a dead ball of ice. It was nothing of the kind. What was it hiding? For 9.5 years, a spacecraft chased a world we were fairly sure would disappoint us. Pluto sits about 3 billion miles out, so far that sunlight takes more than 5 hours to arrive, and the sun shows only as a brilliant star. It is smaller than our own moon, ancient, and frozen near 230 degrees below zero. Everything about it said dead. A small, cold, old body that far out should be a cratered ball of ice, its surface scarred and unchanged for billions of years, geologically finished long ago. The craft, New Horizons again, had launched in 2006 and crossed those 3 billion miles in 9.5 years, only to rip past in a single afternoon, with no way to slow down. In July of 2015, it sent back the opposite of dead: mountains and glaciers, a hazy sky, and across one face a vast pale heart, later named for Clyde Tombaugh, the man who found Pluto in 1930, that turned out to be the strangest thing of all. The left half of that heart is a plane called Sputnik Planitia, a sheet of frozen nitrogen about 1,000 miles across, wider than the state of Texas. The first thing that stunned everyone was what was missing from it. There are no craters, not one. In a solar system where every ancient surface is pocked with impact scars built over billions of years, this enormous plane is blank. Only a surface being constantly remade could stay that way. The nitrogen ice is slowly boiling over, warmed faintly from below. It rises in the center of great cells, spreads, cools, and sinks at the edges, then rises again, turning the whole plane over and erasing any crater before it can last, the way a pot of thick porridge churns on a low flame. Each cell is tens of miles wide, and each full turn takes around 500,000 years. Read the missing craters the way we read them elsewhere, and the surface comes back younger than 10 million years, an eye blink against the rest of the solar system, repaved many times over while everything around it grew old. A churning surface needs heat, and Pluto should not have any to spare. It is tiny. The sun is useless out there, and a small body that ancient should have bled its warmth into space ages ago and locked solid. The heat it does have comes from inside, from radioactive elements in its rocky core that have been slowly decaying since the world formed, a faint, steady warmth leaking outward. The thick shell of ice over that core works as insulation, holding in the little heat there is, the way a blanket of snow keeps the ground beneath it from freezing as hard as the open air. So the warmth driving all of this owes nothing to sunlight. That alone moves a line we did not know was movable. We had assumed a world needs the sun, or sheer size, to stay active. Pluto needs neither. The deeper surprise is where that heart sits. Sputnik Planitia lies almost exactly on the line, pointing straight away from Charon, Pluto's large moon, and a feature like that does not land in so precise a spot by chance. A great basin filled with ice is lighter than the rocket replaced, and lighter regions drift toward the poles, not the equator. For the basin to sit where it does, there must be extra mass hidden beneath it, something dense enough to outweigh the missing rock. The leading candidate is a liquid water ocean. A layer of liquid water under the ice, heavier than the frozen crust, would supply exactly the extra weight, and its bulge would have slowly tipped the entire planet over until the basin rolled into place. Cracks splitting Pluto's surface fit the same story, the stretching you would expect if an underground ocean were slowly freezing and swelling the shell from within. Pluto's moon Charon carries the same hint in another form, a belt of enormous canyons torn across it, the kind of cracking you get when an ocean inside freezes, expands, and splits the crust. None of this is proven, but the best explanation for the position of a frozen heart, 3 billion miles from the sun, may be a hidden sea. The rest of Pluto refuses the word dead just as flatly. The mountains ringing the plain are not rock in any ordinary sense. At Pluto's cold, water ice is hard as granite, so those peaks are mountains of water ice standing like bedrock, while the nitrogen between them is soft enough to flow, creeping into the basin in slow glaciers. Overhead hangs a thin nitrogen atmosphere stacked with layers of bluish haze, and one broad mound, over 100 miles across and miles high, may be an ice volcano, built where slush pushed up from below and froze. Pluto is even bleeding its thin air into space, some of it drifting onto Charon and staining that moon's north pole a deep red. I keep thinking about how confidently we had filed Pluto away as inert, a frozen full stop at the end of the solar system. It took one flyby to show that the confidence was about distance, not about Pluto. The smallest, farthest, coldest world we have had a close look at turned out to be among the most alive. That is the real lesson of the heart. Warmth and motion, even the chance of liquid water, do not require a nearby sun. A world can carry its own heat for billions of years, sealed under ice, far past anywhere we thought geology could reach. We now suspect the solar system is dotted with buried oceans under the ice of several moons and maybe more than one dwarf world, holding all together far more liquid water than sits on the entire surface of the Earth, almost none of it ever touched by sunlight. Pluto keeps its warmth faintly, from within. But closer to the sun there are moons that are not warmed gently from inside, but squeezed hard from outside, kneaded by the gravity of a giant. What could that kind of heat be keeping liquid? Pluto held its warmth faintly, leaking it out from a rocky core. The moons we turn to now are warmed the opposite way, not from within but from without, gripped and worked by the gravity of the largest planet in the solar system. In 1979, the Voyager spacecraft reached Jupiter, a world so vast that more than 1,000 Earths would fit inside it, 5 times farther from the sun than we are. It's like taking 3/4 of an hour to reach us. Voyager's first gift was Jupiter itself, a banded, storming atmosphere carrying a single hurricane wider than the whole Earth, the Great Red Spot, which has been spinning for at least 150 years with winds near 300 miles an hour and no sign of stopping. Around the giant circle dozens of moons, and the expectation for them was the usual one for anything that far out. Old, cold, cratered rocks, frozen and finished. Voyager flew in close, and 2 of those moons rewrote what a small world that far from the sun is allowed to be. The first was Io, and it should not have been possible. A navigation engineer named Linda Morabito, checking a routine image to fix the spacecraft's position, noticed a strange smudge rising off the moon's edge. It was a plume, an erupting volcano, throwing material hundreds of miles into space. Io was not a dead rock. It is the most volcanically active body in the solar system. Its surface, a churning skin of sulfur in yellows and oranges and reds, dotted with hundreds of active volcanoes and lakes of molten rock, repaved so constantly that it carries almost no impact craters at all. Its lava runs hotter than anything that erupts on Earth today, and its tallest plumes climb 200 miles before raining sulfur frost back down. The strangest part of the discovery is its timing. Days before Voyager arrived, 3 scientists had published a calculation predicting that Io should be heated and melting inside, for a reason almost no one had taken seriously. They had worked out, on paper, that this moon would be on fire. The reason is the grip of Jupiter itself. The giant's gravity raises a bulge in Io's solid body, the same way the moon raises tides in our oceans. Except here, the tide is in rock. As Io circles Jupiter, that bulge flexes, and the surface of the moon heaves up and settles down by as much as 100 meters with every orbit, the height of a 30-story building rising and falling in solid ground. All that flexing grinds the interior against itself, and the friction releases heat, enough to melt the rock and feed the volcanoes. Pour it all together and Io leaks more warmth than it could ever receive from the distant sun, glowing in the infrared from the heat of its own grinding. One problem nags at the picture. A moon on a perfectly circular orbit would hold a steady bulge and barely flex at all. For the kneading to continue, Io's orbit has to stay slightly stretched, and on its own it would have rounded out and gone quiet long ago. What keeps Io's orbit from settling is the company it keeps. Io, Europa, and Ganymede, the three large inner moons, are locked into a clean rhythm. For every single trip Ganymede makes around Jupiter, Europa makes 2 and Io makes 4. Lined up that regularly, the moons tug on one another at the same points again and again, and those repeated pulls keep all 3 orbits from rounding out, holding them slightly off circle. So the heat inside Io does not come from Jupiter alone. It comes from the gravitational conversation among the moons, each one's pull feeding back into the flexing. The arrangement even explains the gradient. Io, closest in and worked hardest, runs molten. Europa, one step out, gets enough to keep an ocean but not to melt rock. Ganymede, farthest, the least of all. One rhythm, 3 very different fates. The same dance reaches the next moon out, and there it does something gentler. When Voyager passed Europa, it found not a cratered rock but a smooth ball of ice, cracked all over with long dark lines and almost free of impact scars, a surface clearly young and reworked. Its face is scored with chaotic, jumbled terrain, blocks of ice that look as though they floated apart and refroze. Voyager could only raise the question. Later spacecraft answered it. Beneath that shell of ice, perhaps 15 miles thick, lies a global ocean of liquid salt water, held from freezing by the same tidal flexing that melts Io, only milder here. The clearest sign came from magnetism, the way Europa disturbs Jupiter's magnetic field exactly as a hidden layer of salty, conducting water would. And now and then telescopes have caught faint plumes of water vapor jetting off its edge. That ocean may hold more than twice the water of every sea on Earth combined, sealed under ice, warmed from below, more than 400 million miles from the sun. An ocean like that has the 3 things life is thought to need: liquid water, a source of energy in the tidal heat, and the chemistry of a rocky seafloor pressed against the sea. Possibly even hot vents where water meets rock, the kind of place where life may have begun on Earth. No one has found anything living there, and it is honest to say we have not truly looked yet, only inferred the ocean from a distance. Spacecraft are on their way to it now to look more closely. What stays with me is that a single force does both jobs without preference. The same kneading that turns Io into a furnace of sulfur is what keeps a quiet sea liquid next door. The heat does not choose what it makes. Out here, far past any warmth the sun can give, gravity alone decides whether a moon becomes a hell or a possible cradle. Voyager did not stay at Jupiter. It used the giant's gravity to fling itself onward, the same kind of slingshot that scattered the Oort cloud long ago, and rode it outward toward the next planet. There it reached the most beautiful object in the solar system, and then, looking closer, found that it is quietly coming apart. The crown everyone knows is dying. How long does it have? In the winter of 1980, Voyager reached Saturn, nearly 10 times farther from the sun than Earth, its light an hour and a half old by the time it returns to us, and turned its cameras on the rings everyone thought they already knew. Up close, the single band split into thousands of separate ringlets, fine as the grooves on a record, made almost entirely of ice, from grains of frost to chunks the size of houses. A few wide gaps cut through them, the largest swept clean by a moon whose pull, repeated in rhythm, flings any stray particle back out, the same kind of resonance that shapes the Kuiper belt. The first thing the data forced on us was the shape, and it is hard to believe. The rings stretch wide enough to nearly span the distance from the Earth to the Moon, yet they are only tens of meters thick. Shrink them to the width of a football field and they would be far thinner than a human hair, a sheet so flat that seen edge-on from far away, they almost vanish. That delicate, impossible-looking sheet is the most famous object in the solar system, and Voyager caught the first sign that it is falling apart. The rings are raining into the planet. Sunlight and Saturn's magnetism slowly charge the tiny ice grains, and once charged, a grain feels the planet's magnetic field as much as its gravity and begins to spiral down along it, falling into the upper atmosphere as a faint, steady drizzle of ice. Voyager saw the first hint as dark bands high in Saturn's clouds. A later spacecraft measured the rate, and it is not gentle. Enough ring material falls in to fill a large swimming pool every half hour, hour after hour, age after age. At that pace, the rings have perhaps 100 million years left, maybe a few 100 million, before they thin away to nothing. Saturn is, in a real sense, slowly eating its own crown. That would be strange enough alone. The stranger discovery is at the other end of their life. When we finally weighed the rings, they came out light, their whole mass adding up to about that of one small moon, and their ice is still clean and bright, barely darkened by the dust that rains onto everything in space over time. Both clues point the same way. The rings are young, likely formed only a few 100 million years ago, long after Saturn itself, at a time when Earth already carried forests and animals and the first dinosaurs. Not everyone agrees, and the debate is open, but the weight of the evidence leans toward youth. So the rings are not an ancient fixture. They are recent, and they are vanishing, and the span in which Saturn wears them is a thin sliver of the planet's life. It unsettles me a little to know we are alive inside that sliver. 100 million years too early or too late, and the most beautiful thing in the solar system simply would not be there to see. Where did a fresh set of rings come from? Almost certainly from something destroyed. A moon or a large comet drifted too close to Saturn and crossed a line called the Roche limit, the distance inside which a planet's tides overpower a body's own gravity holding it together. Closer than that line, the planet pulls harder on the near side of an object than on the far side, stretching it until it can no longer keep its own shape, and it comes apart. The debris spreads into a flat sheet, each piece settling into its own orbit, grinding against its neighbors until what remains is a smooth disk of ice. The rings mark that edge in space. Every one of them lies inside the line, and just beyond it the moons begin. The same boundary that forbids a body from holding together is where, a little farther out, loose ice is finally free to gather into one. Ring on the inside, moon on the outside, divided by a single line. Within that disk, Voyager found a level of order no one expected. The thousands of ringlets are kept in line partly by tiny moons set among them. A small moon orbiting just outside a ring nudges stray particles back in, and one just inside nudges them out, the pair herding the ice into a sharp-edged band the way two dogs hold a flock between them. Some of the ringlets are not even circles, but tight spiral waves, ripples raised in the ice by the pull of distant moons, standing in the disk long after the moon that made them has moved on. Then there were the spokes. Voyager photographed dark, ghostly streaks running straight across the rings like spokes on a wheel, appearing and fading over a few hours. They should not exist. The inner part of a ring orbits faster than the outer part, so any straight feature ought to smear into a curve within hours. The best answer is that these are clouds of fine dust lifted just above the rings by electric charge, riding Saturn's magnetism, briefly defying the orbits below them before settling back, a puzzle Voyager raised that we are still not finished with. Saturn keeps one more secret that touches the thread we have been following. Among its moons is a small, bright one called Enceladus, and from cracks across its south pole it sprays fountains of water vapor and ice hundreds of miles into space, some of it feeding one of Saturn's faint outer rings. That water comes from a hidden ocean beneath its shell, kept liquid by the same tidal flexing we met at Jupiter, another buried sea far from the sun. When a spacecraft flew through that spray and tasted it, it found not only water, but salts, organic molecules, and grains of silica that form only where hot water meets rock. The fingerprint of warm vents on a seafloor we will never see. So Saturn holds both endings at once. A crown of ice quietly raining away, and a tiny moon flinging a possible cradle of life out into the dark. The rings will be gone in a geological eye blink. The ocean may outlast them by billions of years. Voyager did not linger at Saturn either. It bent around the planet and pressed on, deeper and colder, toward a world it would not reach for almost another decade. What it found there broke the simplest rules we had about how a planet should sit and spin, a world knocked onto its side, and a moon that looks as if it was shattered and clumsily put back together. Why is this planet lying down? Picture the planets as spinning tops, each turning more or less upright as it circles the sun. Then there is Uranus, which is not spinning upright at all. It lies on its side, tipped over by about 98 degrees, rolling around its orbit like a ball, instead of turning like a top. Uranus was the first planet ever found with a telescope, spotted in 1781, and when Voyager 2 finally reached it in 1986, after a flight of nearly 2 billion miles, the planet looked almost blank, a smooth, pale blue-green ball with barely any weather, its color the work of methane high in the air soaking up red light. No spacecraft has visited it before or since. A planet on its side keeps seasons unlike anywhere else. Each pole points almost straight at the sun for about 42 years of unbroken daylight, then swings away into 42 years of night. Nothing about how a planet is supposed to sit prepared us for this, and the tilt is only the first of its broken rules. The 98-degree tilt is the spin, the angle the whole planet rolls at. The magnetic field is a different problem entirely. On Earth, the magnetic poles sit close to the spin poles, near the top and bottom, and the field runs roughly through the planet's center, which is why a compass works. Uranus refuses both. Its magnetic field is tilted about 59 degrees away from its spin axis. And on top of that, the field does not even pass through the middle of the planet. It is shoved off to one side, anchored about a third of the way out from the center. So as Uranus turns, the whole field lurches and tumbles around with it, a wildly off-kilter shape sweeping through space. The consequence is that its magnetic shield swings open and slams shut as the planet rotates, letting the solar wind in and out in a way no other world does. A field that crooked points to where it is made. Earth's magnetism comes from a churning core of molten iron, deep and centered, which tends to make a clean, centered field. Uranus has no such core to speak of. Under its thin outer atmosphere lies a vast, dense layer of water, ammonia, and methane, squeezed so hard that it behaves like a hot, electrically conducting fluid, a charged slush rather than a metal. The field is generated in that shallow shell, churning near the surface instead of deep at the center, and a dynamo running in a thin outer layer naturally makes a lopsided, off-center field. The pressures down there do something stranger still. They tear methane apart and free its carbon, which under that crushing weight is thought to squeeze into diamond, drifting down through the interior in a slow rain that may pile into a layer thousands of miles deep. Neptune, the next planet out, runs nearly the same way, which tells us this is not a freak of one world, but how both ice giants are built. That still leaves the bigger question. What knocked the planet over in the first place? The leading answer is a blow. Early in the solar system's history, something close to the size of the Earth is thought to have slammed into Uranus and tipped it almost flat, a single collision the planet never recovered its footing from. The strongest clue sits in its moons. They orbit neatly around Uranus's tilted equator, lying in the same plane as the sideways spin, exactly what you would expect if they formed from a disk of debris thrown up by the impact after the planet was already knocked over. It is not the only idea. A slow tug from a long-lost large moon could in principle have done it, but the impact fits the most evidence, and the tidy plane of the moons is its strongest support. The same blow may explain another oddity, that Uranus gives off almost no heat of its own, far less than the other giants, as if its inner warmth were knocked loose and lost long ago. I used to read the solar system as a tidy machine, every planet upright and in its place. Uranus is the reminder that the tidiness is partly luck, that one bad morning 4 billion years ago can leave a world on its side for good, with nothing to ever stand it back up. The wreckage of that violent youth shows in its moons up close, and one of them is among the strangest objects Voyager ever photographed. Miranda is small, only about 300 miles across, and its surface looks like several different worlds broken apart and shoved back together. Smooth, ancient plains sit hard against jumbled belts of grooves and ridges with no blending between them. The strangest features are 3 great oval patches, like racetracks pressed into the surface, ridges and furrows wound around quiet centers, found nowhere else in the solar system. Cutting across it is a cliff called Verona Rupes, a sheer drop of perhaps 12 miles, more than twice the height of Everest, very likely the tallest cliff anywhere we know. In Miranda's feeble gravity, you could step off the top and fall for around 10 minutes before reaching the bottom. For a long time, the assumed story was that Miranda had been shattered and reassembled. The better answer now is gentler. Long ago, its orbit was caught in a rhythm with another moon, the same kind of resonance that heats Io, and the flexing warmed Miranda's interior just enough to push fresh material up to the surface in patches, leaving the seams we see. Everything we know about all of this rests on a single afternoon. Voyager 2 flew past once, in 1986, and nothing has returned since. So a whole planet and its moons remain a decades-old snapshot, a world we studied for one day and have watched from far off ever since. We are finally planning to go back, to settle what one fast pass could only hint at, though that mission will not arrive for decades. What we did see was a planet knocked askew, its field tumbling, its moons stitched from scars. Order, out here, is not a law. It is whatever survived the early chaos. Voyager pressed on from Uranus to the last planet of all, the farthest and coldest, where you would expect nothing to move. Instead, it found the fastest winds in the solar system. What could be driving them so far from the sun? Neptune is the last planet, 30 times farther from the sun than the Earth, so distant that sunlight takes 4 hours to arrive and lands more than 900 times weaker than it does here. At that distance, the sun is little more than a very bright star, and noon on Neptune is dimmer than dusk on a cloudy day. Neptune is also the one planet we found with mathematics before we ever found it with a telescope. In the 1840s, astronomers noticed Uranus drifting slightly off its predicted path, worked out that an unseen world must be tugging it, and aimed their telescopes exactly where the equations pointed. Neptune was there. Everything about the place says still and frozen, a world starved of light that should barely stir. When Voyager 2 arrived in 1989, the last planet it would ever visit, it found the opposite. Neptune carries the fastest winds anywhere in the solar system, streaming around the planet faster than the speed of sound. Winds like that need energy, and out here there is almost no sunlight to give it. So what is driving them? The energy is coming from below, not above. Neptune gives off far more heat than it receives, radiating something like 2.5 times the warmth it gets from the distant sun, a sign of a powerful source of heat deep inside. That internal warmth rises through the atmosphere, stirring it from the bottom, and with almost no sunlight to even things out, The heat from within drives the weather nearly on its own. Voyager caught the result as a vast storm, a dark oval as wide as the Earth that came to be called the Great Dark Spot. Those dark spots are not storms the way a hurricane is, but huge clearings punched down into the cloud deck, often trailed by bright methane clouds riding the winds at their edge. Unlike Jupiter's red storm, which has raged for centuries, Neptune's was gone within 5 years, vanished by the time the next telescope looked. The heat driving it is most likely warmth left over from the planet's own formation, still leaking out billions of years later. That raises a problem the moment you set Neptune beside Uranus. The two are near twins, almost the same size, almost the same makeup, neighbors at the cold edge of the planets. Yet one of them gives off almost no heat at all, and the other glows with more warmth than the sun delivers to it. Same kind of planet, opposite hearts. One idea is that Neptune's interior churns freely and carries its heat up, while Uranus settled into stable layers that bottle its warmth in, perhaps sealed off by the same ancient blow that tipped it over. But that is a story we reach for, not one we have nailed down. What I keep turning over is how little it seems to take to make two nearly identical worlds this different. One runs cold and silent, the other roars with the fastest winds in the solar system, and we still cannot say cleanly why. Neptune's largest moon broke a different rule. Triton orbits the planet backward, circling against the direction Neptune spins, and it is the only large moon in the solar system that does. A moon that forms alongside its planet inherits the planet's spin and travels the same way. A moon going the other direction did not form there at all. Triton was captured. It almost certainly began as a free body out in the Kuiper Belt, a cousin of Pluto, until it strayed too close to Neptune and was caught and dragged into orbit, looping backward ever since. Catching a moon is not easy. A passing body usually swings by and leaves, so to be held, Triton had to shed a great deal of energy fast, probably by plowing through and wrecking whatever moons Neptune already had. That same violent capture would have flexed and heated Triton fiercely, perhaps melting it straight through, which is part of why it is still alive today. And the captured moon is alive. Triton's surface sits near 38 degrees above absolute zero, among the coldest places ever measured. Cold enough that nitrogen, most of the air you are breathing right now, lies frozen solid as ground. Yet Voyager photographed dark plumes rising from it, geysers venting nitrogen gas several miles up, their fallout streaked downwind across the ice, a world that cold should be inert, and it is erupting. The likely engine is faint and clever. Weak sunlight passes through the clear surface nitrogen like light through a pane of glass, warming darker material just below until the trapped nitrogen flashes to gas and blasts out through any crack it can find. Much of the surface is dimpled into a pattern that looks like the rind of a cantaloupe, found nowhere else, and the geyser streaks all point one way, combed out by thin winds in an atmosphere almost too faint to call one. Triton may even hide a liquid ocean beneath its crust, warmed by the heat of its own capture, one more buried sea at the rim of the planets. That capture came with a sentence. Because Triton orbits backward, its motion is slowly dragging it inward, closer to Neptune with every pass, and in a few billion years, it will cross the same kind of line that shredded a moon into Saturn's rings. When it does, Neptune's gravity will tear it apart, and the last planet will gain a bright ring of its own from the wreck of a stolen world. Neptune already wears a set of faint, dusty rings, one of them clumped into strange bright arcs, so it has a small head start on the crown Triton will one day become. But Neptune is the end of the planets, not the end of the sun's reach. Past it, Voyager kept going, out of the realm of worlds entirely, toward the place where the sun itself finally runs out. Where does that happen? And what does the edge of the sun's reach actually look like? The sun's reach does not end at the last planet. Long after the planets, The sun keeps pushing outward, not with light or gravity now, but with a wind, a steady stream of charged particles blowing off its surface in every direction at once. That wind inflates an enormous bubble around the whole solar system, and the edge we are after is the wall of that bubble, the place where the sun's wind finally loses its push and stops. It sits about 18 billion kilometers out, so far that its light takes 17 hours to reach us. We know exactly where it is, because we have been there. 2 spacecraft launched in the 1970s have crossed it. The first in 2012 and the second 6 years later. The 2 crossings did not even happen at the same distance. One spacecraft punching through a little nearer than the other, a sign that the bubble is lopsided and breathing rather than a fixed sphere. Of every edge in this whole story, this is the only one a human-made object has ever physically passed through. Start with the wind itself. The sun is constantly boiling off its outer layers, flinging charged particles into space at around 1 million miles an hour, a gale of plasma that never stops. That gale streams outward and carves a cavity in the thin gas that drifts between the stars, holding the interstellar medium at arm's length. The bubble it blows is the heliosphere, and the sun and all its planets ride deep inside it. And the bubble is moving. The whole sun drifts through the gas of the galaxy at tens of thousands of miles an hour, so the heliosphere is shaped by that motion, blunt on the side facing into the flow and likely drawn out into a long tail behind, more like the shape of a comet than a ball. Whether it is a tidy comet shape or something stranger is still argued over. The edge itself, the heliopause, is simply where the wind's outward push finally matches the inward pressure of the gas between the stars, where neither can advance and the sun's influence as a wind comes to an end. The crossing is not a clean line, and Voyager found that out the hard way. Well before the true edge, the spacecraft hit a first shock, where the supersonic solar wind suddenly slams to a crawl as it begins to feel the gas ahead. You can watch the same thing in a kitchen sink, where the thin sheet of water from the tap races across the basin and then leaps into a standing ring at the line where it abruptly slows. Past that lies a wide, churning zone of piled-up, slowed wind, turbulent and hot, stretching billions of miles before the real boundary. And the magnetic field out there does not lie flat. It breaks into a froth of huge magnetic bubbles, each one as wide as the distance from the Earth to the Sun, a sea of them jostling at the rim. So the edge of the Sun's domain is not a wall you cross in an instant. It is a thick, restless frontier, layered and bubbling, that takes years to pass through. Knowing the exact moment Voyager crossed took a piece of luck and a clever ear. The instrument built to measure the plasma directly had failed years before, so the team could not simply read the density off a dial. Instead, they listened. When a burst from the sun, a shock wave thrown off by a flare, washed over the spacecraft, it set the surrounding plasma ringing, and the pitch of that ringing depends on how dense the plasma is. Thin solar wind plasma rings at a low pitch. The denser, colder plasma between the stars rings higher. When the note jumped up, they had their answer. The spacecraft had passed out of the sun's wind and into the gas of the galaxy. The other signs followed, a sharp drop in particles from the sun and a sudden rise in cosmic rays from deep space. The radiation the bubble had been shielding us from all along. That shielding matters more than it sounds, because the bubble blocks most of the galaxy's hardest radiation, and without it, every planet, including ours, would take a far heavier dose. And then the boundary did something no one ordered. The sun's magnetic field and the galaxies were expected to point in clearly different directions, so crossing from one into the other should have shown a sharp swing in heading, a clean change marking the line between inside and out. The field barely turned. On both sides of the boundary it pointed nearly the same way, as though the galaxy's field near our door were lined up with the sun's far more closely than any model allowed. No one fully expected it, and no one has fully explained it since. What lands hardest for me is where that surprise came from. Not some distant galaxy at the limit of sight, but the doorstep of our own house, the single boundary we finally reached out and touched, and even it behaved in a way we did not predict. We had also learned to map this whole rim without going there, catching atoms that fly back inward from the boundary and drawing its shape from Earth, which turned up a bright, narrow ribbon arcing across it that no one saw coming and no one has cleanly explained. It is worth being clear about what the spacecraft did and did not leave. They crossed out of the sun's wind into interstellar gas, and in that sense they are now in interstellar space. But they have not left the solar system, because the sun's gravity reaches thousands of times farther still, out to that frozen shell of comets we spoke of long ago. It would take the spacecraft about 300 years just to reach the inner edge of that shell, and roughly 30,000 to come out the far side, by which time their voices will have been silent for hundreds of centuries. So the machines are beyond the sun's wind, deep in the dark, still moving, and still, against all odds, speaking to us. Then one of them began sending back nonsense. Was it finally dying 18 billion kilometers from anyone who could help? In late 2023, the older of the two Voyagers stopped making sense. It was still there, still pointed the right way, still receiving the commands we sent. But everything it sent back had turned to nonsense, a single meaningless pattern of ones and zeros repeating over and over, with no readable word about its instruments, its health, or anything it was sensing. From 24 billion kilometers away, a machine 46 years old had started speaking in static. It was not the first scare. A year earlier, the same spacecraft had begun reporting impossible readings about its own position, a fault traced to a different dead computer and quietly routed around. This time was worse. The first fear was the simple one. After all that time in the cold and the radiation, the spacecraft was finally dying, and there was no one within a 2-day reach who could do a thing about it. To understand how hard that is, start with the distance. A command sent to Voyager travels at the speed of light and still takes about 22.5 hours to arrive. The reply takes the same time coming back. Every single question, then, is a 2-day conversation. You send an instruction. Wait nearly a full day for it to land. Wait another full day for the answer. And only then learn whether the thing you tried did anything at all. The signal itself is almost nothing by the time it reaches us. Voyager transmits with about the power of a refrigerator bulb, and after 24 billion kilometers that whisper arrives as roughly a billionth of a watt, caught only by some of the largest dish antennas on Earth. All the energy its signal has delivered across nearly half a century would not light a small bulb for even a second. And it trickles in slowly, a few hundred bits a second. Slower than the first home modems, so even a full status report takes hours to assemble out of the dark. Finding the fault inside that whisper took months. The trouble traced to a single failed chip in one of the spacecraft's computers, a piece of memory holding part of the code that packaged its data for the trip home. When that chip died, the code it carried was corrupted, and everything downstream came out as garbage. No one could open the computer and look. They had to reason out which chip had failed and what code it had been holding, purely from the pattern of the nonsense coming back, like diagnosing an illness from one garbled word repeated down a bad phone line. These are not modern machines. The whole spacecraft runs on computers with less memory than a single photo on your phone takes up, built and programmed in the early 1970s. And there was no replacing the chip. Nothing can be touched out there. The only tools left were words, sent across that 2-day gap to a patient that could not be seen and could not be opened. What the engineers did next is the part that stays with me. They could not fix the broken chip, so they decided to work around it. The corrupted code had to live somewhere, and its old home was gone. So they rewrote it and broke it into pieces small enough to tuck into the unused scraps of memory scattered across the rest of the system. Each test was the same slow ritual. Send a fragment, wait the better part of 2 days for the round trip, read the reply, decide the next move, send again. The code they were rewriting had been written by hand, in a language few still use, by people most of whom were no longer there to ask. Then, in the spring of 2024, a signal came back that was not nonsense. The machine was reading its own instruments again and reporting cleanly, its voice restored by people who had rebuilt its mind in pieces, blind, from a third of the way to interstellar space. The repair bought time, not a cure. Voyager runs on the slow decay of a lump of plutonium, and that source weakens by about 4 watts every year. So one by one its instruments are being switched off to keep the rest alive, like dimming the lights in a house to keep the heat on. It was built to last 4 or 5 years, just long enough to reach the outer planets, and it has now run more than 9 times that. Its cameras were shut off decades ago to save power, so it has been flying blind for most of its life, feeling its surroundings rather than seeing them. Within the next decade, the power will fall too low to run anything at all, and the spacecraft will go silent for good. The people keeping it talking work partly from documents written in the 1970s, since many who built it have long retired or died, and the knowledge survives in fading manuals and a handful of memories. There is a tenderness in this I did not expect from engineering. A small team, some of them reading notes older than they are, coaxing a dying machine to hold its voice a little longer, knowing the day is coming when no command they send will ever be answered. For this whole journey we have used machines to reach one edge after another, and here the machine itself sits at an edge, just past the limit of what we can still touch. We built something that outran our own reach, and keeping a single thread of contact has become an act of care against the dark. But this same spacecraft, long before its memory began to fail, long before it crossed the wind's edge, did one last thing while it could still see the planets. It turned its camera around, back the way it had come, and looked at us. What does everything we have ever been look like from out there? On Valentine's Day of 1990, from 6 billion kilometers out, Voyager turned its camera around and took a picture of home. From that distance, more than 30 times the Earth's distance from the Sun, the planet that fills your whole sky shrank to a point you would miss if you blinked past it in the frame. In the image, the Earth is not a globe. It is a single point of pale light, less than 1 pixel wide, a tenth of a single dot, hanging in the dark. Everything you have ever known is inside that speck. Every ocean, every city, every person alive that day, folded down into a fleck you could cover with the smallest mark. And it was nearly the last thing the spacecraft ever saw. Within weeks, its cameras were switched off for good, to save power for the long road out. Of all the images it sent back across 13 years, the final one it bothered to take was of the place it left. That photograph almost never happened. It carried no scientific value at all. The cameras would have to point back toward the Sun to catch the inner planets, and a bright enough beam straight down the lens could have blinded the instruments for good, so the cautious decision was not to bother. One astronomer on the imaging team kept pushing for it anyway, arguing that the picture was worth taking not for what it would teach us about the Earth, but for what it would show us about ourselves. The team waited until the spacecraft was far enough out that the Sun had shrunk to a safer point, then sent the command, knowing this would likely be the last set of images Voyager ever made. He was right in a way that has nothing to do with data. There is no measurement in that frame. Its whole worth is a point of view, the one perspective no instrument aimed outward can ever capture, the sight of everything at once, from far enough away to see how little room it takes up. There is a detail in the picture people often misread. The Earth appears to hang inside a soft shaft of light, as though caught in a beam lit from somewhere. That band of light is sunlight scattering inside the camera's own optics, a streak of glare thrown across the lens because the cameras were aimed so near the sun. The Earth simply happened to fall inside one of those stray streaks, by pure chance, the way a speck of dust drifts into a sunbeam slanting through a window and lights up for no reason at all. So the most quoted image of our place in the universe frames us in a beam that is an accident of the lens. No one arranged it. We were not picked out. We landed, by luck, in a smear of scattered light. By modern standards, the picture is crude, low, and grainy, shot through a kind of television tube long, obsolete, and its power was never in sharpness. A blurry dot was enough. Hold still on what that fleck contains. Every human being who has ever lived, something like 100 billion people across all of history, spent their whole lives on that one point of light. Every empire that rose and fell, every war fought over every border, every language and every song and every quiet, ordinary afternoon, all of it happened there, on a dot too small to find, unless someone shows you where to look. And the closeness is the part that catches people off guard. 6 billion kilometers is almost nothing on the scale of this story, where galaxies sit billions of years away. From a vantage that is, cosmically, barely across the street, the whole of human history had already shrunk to a smudge. Pull back to any real cosmic distance, and the dot does not get smaller. It simply vanishes. There is one more thing about that dot, and it is the part that stays with me. Light from the Earth took about 5.5 hours to cross the distance to the camera, so the planet in the picture is not the planet as it was when the shutter opened. It is the Earth of 5.5 hours earlier, already moved on, already changed, by the time its light arrived. Even our single self-portrait is slightly out of date, an image of a home that had become a little different before the picture even formed. The dot does not sit alone either. Mars was too thin a crescent to catch, and the inner worlds were lost in the sun's glare. But Jupiter, Saturn, Uranus, Neptune, and the Earth all came through, each a faint speck, the family of the sun lined up for the only group portrait it will ever have. We hold sharper pictures of distant galaxies than the one we have of our own home. That was the camera's last act. It looked back once, caught us by accident in a stray beam, and then closed its eye for the rest of the journey. But the spacecraft was never only a camera. Bolted to its side, it carries something we put there on purpose, a message meant to outlast the dot it photographed, to outlast the planet, perhaps to outlast our whole species. If you had one chance to tell the universe who we were, knowing it might be opened long after we are gone, what would you send? What we sent is a record, in the old sense, a disc meant to be played. Bolted to the side of each Voyager is a gold-plated phonograph record, sealed in a case, carrying a portrait of Earth for whatever might one day find it. There are 2 of them, one on each spacecraft, identical, each case engraved with instructions for how to play it and a stylus tucked alongside, in case the finder has never seen such a thing. It was put aboard knowing it would almost certainly never be read by us, and might never be read by anyone. A message dropped into the largest ocean there is, with no expectation of an answer. On it is not a list of our achievements, or our weapons, or our wars. It is something quieter. It is what a small group of people decided, in 1977, was worth saying about being alive on this planet, to a stranger who would share with us nothing at all except the same physics. They began with voices. Greetings in 55 languages, spoken plainly, hello and welcome and peace, from a child's voice to an old one. Then the sounds of the world itself, with no words, wind and thunder and rain, surf breaking, a heartbeat, footsteps, a kiss, the cry of a newborn, the long calls of whales speaking across an ocean. Then the music, about 90 minutes of it, gathered from every corner of the earth. A German composer's strings beside a blues guitarist's lament, a Peruvian wedding song beside drums from Senegal, beside a night chant from the Navajo. Encoded into the same disc, in a form a patient mind could decode into pictures, are more than 100 images: a fetus, a nursing mother, a desert, a city, a page of mathematics. The makers chose to show our gentlest face, no cruelty, no famine, a hopeful self-portrait rather than an honest census, which was its own quiet decision about what we wanted to be remembered as. One of the people making it recorded her own brain and heart, the electrical storm of a mind thinking through what it is to be alive and in love, and pressed that hour of being a person into the grooves. The hardest problem was the cover, because a finder would share no language with us, not a single word. So the makers wrote in the only language they could rely on: physics. Etched on the case is a map, but not of streets or coastlines. It marks the position of our sun against 14 distant pulsars, those dead stars that flash with a precise, steady beat, each one labeled by its exact rhythm. Because every pulsar slows in its own predictable way, a finder could read not only where the record came from, but when it was launched, working out our home and our moment from the flicker rates alone. Every measurement on the cover is anchored to a single fact about hydrogen, the commonest atom in the universe, which flips between two states and gives off a signal at a fixed wavelength. We met that same signal far back, the 21-centimeter note of hydrogen we use to listen for the cosmic dark ages, and here it serves as a universal ruler and clock, the one unit any physicist anywhere would already know. Beside the map sits a patch of uranium, placed there as a clock of its own. The metal decays at a known pace, so by measuring how much is left, a finder can count the years since it left Earth, the way the sand, still in an hourglass, tells you how long it has been running. The records are going nowhere fast, and everywhere slowly. Neither Voyager is aimed at a star. They are simply falling outward through the galaxy, and the empty distances are so vast that even a near miss takes ages. In about 40,000 years, the first will drift within roughly 1.5 light-years of a faint star in the northern sky, closer to it than to our own sun, though still far enough that the star would be no more than a bright point. The second will pass within a few light-years of Sirius in something like 300,000 years. And the records may outlast almost everything that made them. Out there, with no weather and almost nothing to strike them, the gold wears down only from the rare grain of cosmic dust and the slow rain of radiation, so gently that a record should still be playable 1 billion years from now, long after the sun has grown bright enough to boil away our oceans and end life on the surface. Here is the part the makers understood and did not hide from. The space between stars is so close to empty that the odds of anyone ever finding either record are almost nothing. They built it anyway, with enormous care, choosing each sound and image as if it would surely be heard, knowing it almost surely will not. It is the oldest gesture there is, a message in a bottle, thrown not into a sea but into the space between stars, where the bottle outlasts the shore that made it. Their clear-eyed care is the part that moves me most. A message sent with no real hope of delivery is not really a letter to a stranger. It is a portrait of who we hoped we were, made by us, for a reader who may only ever be us. We spent this whole journey reaching toward edges we could not cross, measuring things we could never touch. At the very last one, we did the opposite. We placed something of ourselves on the far side of every edge, on purpose, and let it go. We started this with a single question, asked of every edge in turn. Each time we reached one, what did we find waiting? By now, the answer is the one the whole journey kept giving. At every edge, we found another edge, a boundary of light, a boundary of time, a boundary of what we could reach, each one opening onto a farther one we could not cross. The universe never handed us a final wall. It kept handing us a horizon. And facing all that unreachable distance, the last thing we did was not to conquer it or measure it, but to send a small gold disk of birdsong and heartbeats out into it, in case. That is enough to rest on, I think. Not the smallness of the dot, but the fact that the dot sang something into the dark anyway. Thank you for staying all the way out to the edge with me, and all the way back. You can let the day go now. The light that left those far places is still on its way here, still arriving while you sleep, whether or not anyone is awake to catch it. Sleep well,